So let's look at the warm-up here. So Hafiz keeps track of how much money he has, and in one fixed annuity investment initiated 10 years ago, he had $218,203 3 years ago, and he now has $256,221. So we're going to use the exp reg, which on our TI-84s is 0 on calc stat, then we do 0. And we're going to calculate the annual yield from his investment. So the key on this one, though, is that we need 2 points. So right now, he's got $256,210. And that is in year 10 from the investment. So the commas there are confusing a little bit, sorry. Now, year 7, which is 3 years ago, he had $218,201. So the moment we have 2 points, we can find an exact match for the exponential regression on our calculator. So I'll just plug that in and come back. So in the end here, we get our annual percentage yield. The annual yield there is 5.5% because A was 1.0549. And the initial investment, sorry, I meant B. And the initial investment is just the A. So according to our calculations, it's 150,000. Now wait a tick. That's not exactly what I got. I got 1.2 right there. But most likely, what's your investment? Most likely the investment was $150,000 somebody put in. So if you put in, if I said $150,000, that's fine too. If you said $150,012, that's also fine too. But practically speaking, my guess is this is where we started because that's nicely rounded. All right, so today what we're going to do is we are going to spend some time constructing mathematical models of situations with our exponential in nature. So just to show you, we're going to do some by hand, and that's going to be a little bit tedious. I want us to be able to see what it's like by hand, but most of it I want you to do with the calculator. And then we're also going to look at something called half-life and decay later. So by the end of our lesson, we will get that. Okay, so this one right here is straightforward. We plug in 2 things, 2 points. So this stuff here goes into L1, this stuff goes into L2, and our calculator will find a perfect fit for 2 pieces of data. Now, of course, the question is, how can we do that by hand? So we're going to go back and use a system of equations. If y'all remember system of linear equations, this is better because it's a system of any equations. In this case, it's a system of exponential equations. So let's see here. Remember that our super secret model looks like this. Y equals A times B to the X power. Y times A times B to the X power. So for one equation, I'm going to plug in the 218,201 and the 7. So that's going to give me one function. So 218,201 is equal to A times B to the 7th power. Again, all I did was take the 200 and plug that in. Now let's repeat the process, but with the other results. 256,211 is equal to A times B to the 10th power. So instead of isolating one of the variables and plugging them in, which is what we can do, and what you may have done with your old things, notice we're just going to do operations one against the other. So notice here, and I'm just to save time, I'm going to write it underneath. I'm going to divide one equation by the other one. Just going to divide one by the other. So I'm going to write the 218,201 underneath, and the A, B to the 7 underneath there. So now we're ignoring that up there, and we just divide like so. Notice what happens. What happens to our A's? Look, A's drop out. They drop out to 1 or cancel out is another way to say it. What about my B's? What happened there? They reduce. This one drops 7, so I just get a 3, and this one drops to all of it gone. So notice my new formula I have. I have B cubed is equal to whatever I get when I plug this into my calculator. So take that, plug it into your calculator. And when I do that, I get 1.17. I'll keep writing a little bit for 197. Okay, and of course, how do we clean that puppy up? All we have to do is take the cube root. And your calculator, you can do it really quick. Just raise to the power of 1/3. And we'll find out what b approximately is equal to. So after I take the cube root, I get 1.05498 ... And that rounds when I subtract the 1. That tells me it's a 5.5% yield. Now, of course, that's not our answer. Folks, we didn't find the answer yet. All I found was my yield. So that means I found B, or the 105.5 is going to go into here. So I need to find out what A is. So all I have to do, just like we did in our previous, when you found a system of linear equations, we just take now this, and I'm going to plug it into one of the equations there. It doesn't matter which one. So I'll just choose to put it into the top. So now I take the 218,201 is equal to A times 1.055 to the 7th power. Now I have to divide both sides by whatever I get when I take that to the 7th power. So A is going to be approximately, and that's just a calculator thing right there, just plug it in. Be $150,000 is my initial. Are we done? No, now we just have to plug it back in. So here's our final result here. Y is equal to 150,000 times 1.055 to the t power or x power or whatever. T for time or x for years, whichever. Now the next part says we're just going to predict how much he would have in 3 years. 3 additional years from now. So now we're just going to take not this here. So notice I'm not going to put 3 into here. What number am I going to put in for t? Okay, so now we can evaluate the function. You can do this with your calculator, but $150,000 times 1.055 to the 13th power. All right, we're going to use our handy-dandy calculators for this next one, and you've already done the whole process. And the whole process is simply this. Number one, we're going to enter stuff into L1 and L2 in stat edit. After that, you're going to go to stat calc. And stat calc, instead of pressing the number 4 for linreg, now we're going to go ahead and press the, I think it's the 0 for the xreg, like that. And it'll find us the data. We're going to also look at it by way of looking at the scatter plot too, which will look like this. And then we'll see what our trend line looks like, or excuse me, our exponential model will look like and how it fits inside there. All right, so once I enter stuff into L1, L2, this is what the graph looks like after I graph it. I've not done the exponential regression yet. Now I need to go to stat calc and then select the 0 for exponential regression or xreg. And then when we do that, we end up getting this as our result. And so we see what A is and B is and C is. So since the instructions say for us to round to the nearest thousands, we end up with this. Y equals 296.177 times 1.079 to the x power. All right, so the next part here says, part B, superimpose the graph of the exponential model on the scatter plot in your calculator and describe how well the exponential curve fits the data. Notice when I do that, it looks like this. And notice it doesn't go through every point. In fact, it barely touches most of them. But it's very, very close. In fact, look at our R values here. Our R square and our R values are very high. And so that tells us that it fits very well. And we can see graphically that they do indeed fit very well. Identifying the initial amount and the growth factor, and of course explaining their meaning. The initial amount A is approximately 296, and this is the expected population in 1960, which is not true, but to our model, that it is true, but in real life it's not. And of course, our B is approximately 1.079, so that means it's a 7.9% growth per year. So the observed minus the predicted. Observed is what happens in real life, how many we actually have, and the predicted is what the model. So this is real life, and this is the model. The predicted is based on our model. All right, so to do that, our observed, of course, we see in 2005 was 7066. So 7066 minus, and we're going to take that, since I saved it as Y1 into my calculator, I'm going to go ahead and subtract that, say Y1 45. So the result here is approximately negative 1900. So how do we interpret this? We interpret this by saying that the observed is 1900 underneath. That's what the negative means. Underneath, below the expected or predicted amount. For some reason, the data is way off there. But as we can see here, we do see that it is significantly lower. But notice here, the next year, we're above our prediction just a little bit. So it looks like it bounces off in the end. Okay, now we're going to follow this trend and extrapolate for today, which of course is dangerous, but still, we'll do it because we live on the edge. So what would that be? 57. And when we do extrapolate, we get this, 22,000. Whoa, I'm way off there. Too many twos there. 22,262 eagles, or bald eagles. So, half-life, as we see here, is just how long it takes for the original quantity to decay to half. And here's an interesting story about polonium. In 2007, the element polonium was in the news when a London police detectives investigated the poisoning of a former Russian KGB agent, Alexander Litvinenko. Since polonium had never been known to be used in a poisoning, the authorities did not look for evidence until weeks after the crime had taken place. As a consequence, they had to work backwards from the evidence to calculate the amount of polonium used in the victim. They made use of the fact that the half-life of polonium is 138 days. 138 days. So detectives in the investigation found polonium in a cup in a hotel that he had visited. Suppose that 4 micrograms were found, and it had been 30 days. So now we have a point, a time, and the remainder. So 30 days and 4 remaining micrograms remaining. Since Litvinenko was there, find how much polonium was on the cup originally. Then we're going to derive a model for this situation. So how to approach this? Well, we know that the half-life is 138 days. And this, by the way, is... oh, did I put that backwards? So lambda is the symbol for half-life. You don't need to know that and use that much, but that's just how it is. 138 days. So here's our parent function. This is the exponential function, y equals ab to the x power. We know that the half-life is 138 days, which means whatever a is, since we don't know what a is, whatever a is, it's going to be cut in half in 138 days. So all I do is take the a and cut it in half, and add 138 days there. So what did I do? Essentially, I substituted in the remaining. Half of it is out after 138 days. So this is going to find me my decay factor. Because notice here, when I divide both sides by a, the a's drop out. And so we're left with this equation that, and I'll switch sides to make it a little bit easier. B to the 138th is equal to 1/2, or 0.5.
So why did you?
So the next part requires me to find, I have to find, so B is going to be equal to the 138th root of 0.5. So that brings us to B being approximately 0.995. So I can interpret this clearly because this is under 1. I can say it's a decay. On top of that, I can actually calculate what the decay factor is. So it's decaying by what's the difference between 1 and this. So it's a really, really small amount, 0.5%. Where did that number come from? Again, if you take 100% and minus the 99.5. Again, I moved the decimal over twice there to get the 99.5, and that's what I get. So it's 0.5% decay. How often is it happening? Well, remember what my units here are. On the 138, it's a day. So it's 0.5% a day. All right, now we're not done because we haven't answered the question. So the question says how much polonium, or find how much polonium was in the cup originally. So now I have to take this and I have to plug stuff back in using two things. I'm going to use my decay factor, and I'm also going to use the 30 and the 4. So back to my original y equals ab to the x power. My y is 4. I have 4 micrograms remaining. A is unknown. I'm going to use the 0.995 here to the power of 4. Why? Because it's, oh, sorry, not 4. 30. Because it's 30 days later. 30 days later, there is 4 micrograms left. Now this next part, I'm just going to divide both sides by this. I don't know what this is, so I'm going to enter that in my calculator in just a second. So I'm just going to say 4 divided by 0.995 to the 30th power. To get an approximate value of A is approximately. So in the end, I get approximately 4.65 micrograms. To begin with. All right, so we have a very, very, very small amount. So let's derive a model for the situation. All we have to do is plug in the A and the B so that we can find our result. So the end result of how many micrograms are remaining, beginning with the amount of 4.65, 0.995, and to the power of x or t, whichever you want to use. T for time is the most common. And that's our result. And some would argue we should put an approximate value there. Next and last problem, example 4, and you'll be working on this one. A certain substance has a half-life of 24 years. In a sample of 80 grams, if a sample of 80 grams is being observed, how much will remain in 50 years when, and then the second question is, when will only 5 grams remain? So the first part is that we're going to find the decay factor from lambda. So we substitute in half-life at 24 years. So there's B. And now from there, we're going to evaluate at 50 years. Now, we don't actually have the model yet, so I'm going to make the model real quick. We know what the beginning amount is. It's 80. So y is equal to 80, and our B is 0.972, and I'm just going to substitute in the 50 years there. We just plug that into our calculator. The part 1 is the answer is 19.34 grams after 50 years. So now the next part, when will 5 grams remain? So that one's going to be the same as previously, but instead of putting a 50 up there, I'm going to put a 5 in for y. So 5 grams is equal to 80 times 0.972 times what power? We don't know. And we're going to evaluate that by dividing both sides by 80 first.